Right. So now we have understood three things. What are the design stress strain curve for concrete in compression to be used as per IS 456? What are the design stress strain curve steel to be used for calculations as per IS 456? We also calculated based on the strain conditions what is the maximum neutral axis depth a particular section can have so that it can ensure just the yielding of steel on the tension side. If I put then more steel, then this yielding may not happen. Okay, so we have calculated three things. Now my idea is to calculate for a particular section, for a particular grade of concrete, for a particular Fy, the grade of steel that is given, to calculate what is the limiting moment of resistance. Okay, or in other words, how much maximum AST that I can put in such a way that I satisfy the strained conditions that are specified by IS 456. Again, what are the strain conditions that are specified by IS 456? The steel should reach this strain, okay, when the concrete also reaches 0.0035. Okay, right? So that's this again. When I fix these two strains, then Xe max is your neutral axis depth. From your previous calculations, we have already found out that is actually Xe max by D. When it is normalized with respect to the effective depth, it is only a function of your grade of steel. Okay. Now for this, we know that the stress strain curve as per your code. Again, if you go back and draw, what would be the because here I have not drawn the stress. So what would be the stress diagram? As per the IS code, it is going to be straight triangular portion and then there is going to be a parabolic portion, right? So this value, what it was calculated was basically CC, which is your 0.36 FCK B XU, right? So that is what we have got it here, okay? And similarly, the stress in the steel, you can put that as this is your stress, okay? This is stress, and when you multiply by area you get your force. That is what we got here. Okay, so let me erase this, right? So this is your balance section. So these are your forces. Again, this location of your CC also is given. See, it is already code has done the calculation and it is giving you what should be the location of your C for the assumed design stress strain curve. So it is by integration we can find out that it is going to be 0.42 Xe max, right? So now all these things are known. Okay. Now what is our goal is to find what is the maximum moment resistance that we can get, or it is also called as limiting moment of resistance. Okay, so when XU becomes Xe max, the maximum moment resistance becomes MU limit. So let's calculate now. If I'm taking moment about this point, okay, so this force is going to act. Okay, so what would be this lever arm? This lever arm is nothing but your D minus 0.42 XU. In this case, XU is XU max. So lever arm is this, right? So that is why we got lever arm here, and this is your CC. CC times your Z. Okay, so you get your moment of resistance. So let me erase this for better clarity. Okay, so now what we are saying here is, okay, if I am taking, let's say, if I am just dividing everything by, let's say, BD. So both sides, if I am dividing by BD square, what will happen? So this side will become, so D, 1, 1B and 1B will get cancelled. And I can write this as 0.36 FCK. Okay, this BD square. So when you simplify this, basically this BD square will finally will come out to this side. So basically you will be left with 0.36 Xe max by T, and then again when you take one more D will get cancelled, so it will become 1 minus 0.42 Xe max by T. Okay, so with simple simplification of dividing by both sides by BD square and then taking the BD square, then you end up with this equation for MU limit only in terms of Xe max by T, FCK and BND. Okay, so if you substitute that, then what we represent this MU limit as basically as some normalized factor which is in terms of this K, which is usually taken that as mu limit by FCK BD square, which is a constant value for a particular grade of concrete and particular grade of steel. So if you see that, this can be calculated again as this. So when you do this, 0.36 Xe max by D and 0.42 Xe max by D. Now Xe max by D, if you go back to the previous slide, so we have got these values. For each grade of steel, my Xe max is fixed, right? So I can go back and plug into this equation that we have simplified and find an expression for mu limit, or in other words K, for different grades of steel. So if you look at that, if you substitute, for example, let's say, how do we get this Fe 500 as 0.133? So if you just go back and put it, so let's do this exercise. Okay, so it's going to be 0.36 multiplied by, if you go back, Xe max by D for Fe 500, how much we got? That was 0.456. So if you substitute that, so basically you get how much? 0.456 and multiplied by 1 minus 0.42 multiplied by 0.456. So if we substitute that, let's see how much we are getting for. This is for, okay, we are looking at this K factor. Okay, so if you substitute that, you will get value equal to 0.36 times 0.456 multiplied by 1 minus 0.42 times 0.456. So you get value of 0.133. So this is going to be your 0.133. Okay. So like this, we can find out values of your limiting moment of resistance, which is expressed as a normalized fashion. Okay. Now you can ask me, why is it is convenient? Because it is unitless, right? So what is the unit for your moment? So let me go ahead and, so unit for moment is, okay, moment has a unit of, okay, force times piston, kilonewton meter, let's say. Okay, and then what is that you have? We are dividing that by, let's say, strength, right? Megapascal, Newton per meter square, for example. We usually read Newton per millimeter square, let's say. So when you divide this by FCK, again you are dividing that by Newton per meter square, right? So I put Newton per meter square, and then again I divide that by meter cube, BD square. So if you substitute that, then it becomes this mu. Let me erase this. So basically, this K factor, the unit will become, everything will get cancelled. So this also I can write that as kilonewton per meter square, FCK, right? So everything will get cancelled, and then you will get a unitless quantity. Okay, so it's a normalized value. So in this way, a normalized capacities can be calculated, right? So, for a particular section, so for example, once your grade of steel is fixed for a single reinforced section, then I can calculate my limiting moment as K times FCK BD square. Okay, for a particular grade of steel. Okay, for example, if I'm using 500 grade steel like what we have been using for previous exercise also, then if this can be fixed. So for any given dimensions of B and H, and this can be calculated, okay, in terms of your effective depth. So this is the expression for your limiting moment of resistance. Okay, right. Now let's say, what is the maximum amount of steel that we can put. So using the same mu limit, now I want to calculate what is the limiting amount of reinforcement that I can put. Okay, it is the same. Uh, okay, so let's do now how we are doing this exercise. Okay, so if you see here again, this we are doing it at ultimate. Okay, at ultimate again, we are making sure that for Xe max, this concrete is going to be at 0.0035, steel is going to be just at this value. Okay, when I put steel less than this value, AST limit, okay, AST limit, then this strain will become more. Then the section will become underimposed. The strain on the tension side will become more. Okay, so this is your compression force. We know that, and this is your tension force, and this has to be in equilibrium, and uh, and the location of your CC is 0.42 Xc max, like what we have discussed. That also we discussed from equations of equilibrium. Then CC should be equal to your TS. Okay, so this is your CC and this is your TS. Okay, so then we know that again when I take this B this side. Now why is that I'm doing this is usually it is written as a PT reinforcement, tension reinforcement PT. Now what is PT limiting? So this is what we have it here. So you see here. So this is your PT limit. So how do we define the PT limit? Is in terms of percentages, 100 times AST limit divided by B times your effective depth D. Okay. So I want to find express AST in terms of PT. In terms of usually the previous exercise also you must have seen 1200 mm square, 7860 mm square. All these things that we divide that by the sectional dimensions to express what is the percentage of the cross section that steel is there. So here in code we don't use a gross depth but we use a effective depth. Okay, it's just a nomenclature. Okay, so the PT limit is expressed. So what I wanted to find out is an expression for this limiting percentage of steel, so that I will ensure that the steel is going to at least just yield. Okay, so that is the idea. So I am equating this compression force to tension force. So then what we are doing is B, we are taking it to this side. So basically, how do we get from here? So I'll tell you. So this AST limit, I want to convert it into PT limit. So we know that PT limit is, so I can divide this by 100 by 100, right? And then both the sides, what I can do also is I can divide them by, okay, and I can divide them by, let's say, BD. So when I divide both sides by BD, then there is no change, right? So then what will happen? This and this will get cancelled, right? Then this 100 AST limit by BD will become your PT limit, right? So then this equation becomes 0.836 FCK XC max by D, and this will become 0.87 FI PT limit. So basically, I am trying to express that area of tension steel in terms of percentage of steel. Okay, that is the only thing that we have done. Okay, so now if you for a particular grade of steel, Xe max by D is fixed, right? So now what I can do, I can go back and plug in the value of Xe max by D and then find out an expression for your PT limit. Okay, so then what happens? So PT limit can be expressed as, so basically this FCK, I want to bring it down here, right? And then you can, if you substitute that, it will become point, and then 0.87 when I 0.36 when it is divided by this 0.87, then this becomes 0.414 Xe max by D. So this is very important expression, which is limit, which is expressing PT limit in terms of Xe max by D. Why is this is important is, again, when we solve for your amount of reinforcement that is required, now for a particular moment resistance, I can directly solve the amount of PT required in form of a quadratic equation, and you can directly solve for it. Okay, so this relationship, please keep that in mind. Now again, for Fe 500, what is Xe max by D? It is 0.456. Similarly, for different grades of steel, your Xe max by D will change, and Xe max by D is only function of your grade of steel. It has nothing to do with your grade of concrete. So please keep that in mind. Okay, so for different grades of steel, again, we can go back and look at, put these numbers and then find out what is your PT limit Fy by Fck. So again, how do we get that for Fe 200? So if you go back, so you multiply 0.414 this value. Okay, how do we get 0.189? Basically, it is going to be 0.414 multiplied by 0.189. 456. So if you substitute that, you get a value of 0.189. Is going to be 0.189. This is your this value. Okay, that we are doing for FE 500. Okay, so now the PT limit again, it because it is expressed in terms of 0.189 as a constant. And if I know the grade of steel and the characteristic strength of concrete, then again I can calculate PT limit for a particular section. Right? Okay. So this is what we got. K values that we got, and then we got this, and we now we have expressed the PT limit in terms of your XC max by D. Okay. Where is this? Okay. So now let's see how we can go ahead and calculate your ultimate moment of resistance. Okay. This is actually procedure is also explained in your IS 46 2000 in Annex G. So let's say our code requirement is whatever the capacity that we have calculated, ultimate moment of resistance, okay, should be greater than the factored moment. This is coming from your analysis. This is coming from your structural analysis. Okay, so you do structural analysis and you get your bending moments at various cross sections. So whatever the capacity that we are providing, that should be greater than your demand. So that is it. At the same time, when the capacity is reached, we also need to make sure that XU is less than XU max at ultimate. Again, why is that? To make sure that the steel is going to yield. Okay, and the yield strain is specified by the code. That's what we saw. It is 0.002 plus 0.87 Fy by elastic modulus. Okay, so this is the procedure. So now let us see. We have to make sure that the amount of steel is put in such a way that the XU that is required to satisfy the equilibrium has to be less than the maximum XU that is going to come from your balanced failure condition. Again, what is that XU max? XU max corresponds to balanced failure condition. Okay. In XU max, we have fixed this to be equal to 0.002 plus 0.87 Fy by ES. Right. So, but in this case, I'm going to put steel lesser than the limiting reinforcement, okay, in such a way that XU is going to be less than XC max, because XU at failure always has to be less than XC max. Okay. So if you substitute your equations of equilibrium, again you get 0.36 FCK XUB and is equal to 0.87, because this has to be achieved when concrete is reaching its failure strain of 0.003, right? So then you can find an expression for a neutral axis depth. Okay, so it is basically, I'm just simplifying this. Okay, in terms of D. So again, basically what we can do is, everything you divide by BD, and here also you divide by BD. Okay, so BB will get cancelled. So then you can find expression for XCBD as 0.87 FIAST by BD divided by 0.36 FCK. This is your expression for your neutral axis depth. Now the moment of resistance, of course, we can calculate. Let's say I am calculating the moment of resistance about this point. So this, okay, so this force will not come. So I'm taking moment about this tension point, okay, or compression. So it is going to be this, and my lever arm is this, and lever arm we know that it is basically D minus 0.42 x, right? So this is your lever arm. So this is your tension force. So tension force multiplied by the lever arm will give me this expression for your moment resistance as 0.87 FIAST and D multiplied by this. Okay, right? So we have to ensure, however, put steel in such a way that XU has to be less than XU max. Okay, this is an important thing. So what I can do is, now I can express again in terms of your normalized quantity. So mu by let's say BD square, which R can be expressed as mu by BD square. Then you can write this in terms of, if you can, again this AST can be expressed in terms of your PT. Now again, what is PT? If you go back, and what is PT? PT is nothing but 100 AST by BD. Okay. So it's the amount of steel in percentage. So we are multiplying the area by 100 and dividing by BD. Okay. So this all this AST can be expressed in terms of now your PT. Okay. And then you can form a relationship between mu by BD square and you can express in terms of this. Okay. So now uh, so you can take this. So basically now if you go back and look at this. So now how do we get from here to here? Okay. So D minus. So you look at this value. So this is very straightforward 0.87 FIAST. And when I take D out, it is going to be 1 minus 0.42 XU by D. So this is when I take D out, what will happen? It will be TS multiplied by D minus 1 minus 0.42 XU by T, right? So this is what I just taken D out here. Now let's see what is that expression for 0.42 XU by D. Okay, so this we have already derived previously. So then it will be okay. So if you go back, yeah. So this is the one. So if you look at this, so 0.42 XU max or XU by D can be represented in terms of PT like this. Okay, so this is 0.414. If I take that as 0.42 XU by D is basically nothing but your PT by 100 multiplied by Fy by Fck. So this is basically 0.42 Xc by D is basically PT by 100 multiplied by Fy by Fck. So if you go back and substitute that, okay, so in this equation, so here we have taken, okay, so this what we can do, this is nothing but your PT by BD 100 FCK. So that's how we get. So we can now express moment of resistance in terms of amount of steel like this. Okay, simple modifications. Again, if I put back here, so this 0.42 XC by D is nothing but your AST BD by Fy by Fck. Okay, so if you substitute that, again I can express my R, which is moment resistance in the form of PT in this form of a quadratic equation. Okay, so because here when I take this PT, then it will become PT square. So this becomes your quadratic equation. Okay, so this one thing you have to note on here in this derivation, what we have made sure is this epsilon st is always going to yield. Okay, when this is going to be greater than epsilon sty that is specified in your IS code. Okay, that then only this stress is going to be 0.87 Fi. Then I can relate everything. The moment your strain is greater than your yield strain that is specified in the code, then only the stress will remain at 0.87 Fi for any strain which is greater than your yield strain. Okay, so this we have to make sure this is valid, this expression is valid, this expression is valid only for under reinforced sections or under reinforced sections. So when xu is less than xu max, then only this expression is valid. Okay, so this is one way. Why is it important is, let's say I want to design the amount of reinforcement. Okay, I know what is the limiting PT limit. Now I can quickly calculate PT limit for a particular section, right? Then if moment is given to me, then I can directly calculate the amount of PT in terms of this equation. Okay, so directly I can solve for this for a particular moment. I can quickly find out what is PT. Then I can make sure that PT is less than PT limit. So that will indirectly tell me that my XU is going to be less than XU max. So then this condition is valid. Right?